What if every black hole in the universe collided? Could such an event signal the end of everything we know, or might it birth something entirely new? Could our universe already exist within a black hole? These questions stretch the boundaries of physics and cosmology, inviting us to explore scenarios that test our understanding of reality itself. To examine this possibility, we must first understand whether the laws governing our universe could ever permit such a collision. The fabric of our universe. The universe as we observe it appears stable, possibly infinite, and expanding at an accelerating rate. This behavior emerges from fundamental cosmological values that define the structure and fate of everything around us. The first crucial parameter is omega, which represents the total density of the universe. Omega encompasses all forms of content: ordinary matter that forms stars and planets, dark matter that binds galaxies together through gravity, and dark energy, the mysterious force driving cosmic expansion. Current measurements place omega at approximately 1, indicating that the universe possesses a critical density. This value suggests a flat geometry extending infinitely in all directions. In such a universe, the prospect of merging all black holes becomes problematic. The accelerating expansion driven by dark energy ensures that cosmic structures continue separating from one another. For black holes to converge, gravity must overcome this expansion, but in a flat, expanding cosmos dominated by dark energy, gravitational attraction cannot prevail over the forces pulling everything apart. The second essential parameter involves the equation of state for dark energy, often represented as a value near -1. This number characterizes how dark energy behaves as the universe evolves. The current value ensures perpetual expansion, with the rate of expansion increasing over time. Should this parameter change significantly, the universe could face dramatically different fates. Some scenarios predict a big rip, where expansion accelerates so violently that it tears apart galaxies, stars, atoms, and eventually even spacetime itself. Other models suggest different catastrophic endings, each dependent on subtle variations in these fundamental constants. Together, these parameters define not only the present state of the universe, but also its ultimate destiny. They determine its geometry, its expansion rate, and whether the cosmos will expand forever or eventually collapse. Understanding these values provides the foundation for exploring how every black hole in the universe might one day merge. Reconsidering cosmic geometry, observations indicate that the observable universe appears flat within the limits of our measurement precision. However, this does not conclusively prove that the entire universe extends infinitely. The cosmos could possess a curvature that becomes apparent only at scales far beyond what we can directly observe. The cosmic microwave background, the afterglow of the Big Bang, contains subtle anomalies that some researchers interpret as evidence for a closed universe, one that curves back on itself like the surface of a sphere. If the universe is indeed closed rather than infinite, it possesses a finite volume and no edge, much like the two-dimensional surface of a sphere has no boundary. In such a geometry, traveling in any direction for long enough would eventually return you to your starting point. This distinction between an open, infinite universe and a closed, finite one becomes crucial when considering the possibility of black hole collisions on a universal scale. Another critical consideration involves the nature of dark energy itself. This enigmatic component began dominating the universe's energy budget only a few billion years ago. For approximately 9 billion years following the Big Bang, matter and dark matter governed cosmic evolution, with gravity slowing the expansion that began with the big cosmos itself. Dark energy's dominance represents a relatively recent development in cosmic history, raising questions about its permanence. Some theoretical models suggest that dark energy may not remain constant indefinitely. It could represent a temporary phase in the universe's evolution rather than an eternal feature. If dark energy's influence were to diminish or reverse, the expansion of the universe could slow, halt, and ultimately reverse into contraction. Under such circumstances, gravity would reassert its dominance, drawing all cosmic structures back together. Galaxies would begin approaching one another. Stars would feel the pull of distant masses, and black holes scattered across the cosmos would start their long journey toward convergence. This transition from expansion to contraction would unfold over timescales almost incomprehensible to human perception. The reversal would require not billions of years, but trillions upon trillions of years, stretching into numbers that dwarf our everyday understanding of time. Yet if such a scenario were possible, it would set the stage for the most spectacular collision imaginable: the architecture of black holes. Black holes come in several distinct classes, each formed through different processes and occupying different scales. Stellar mass black holes arise from the deaths of massive stars. When a star many times more massive than the Sun exhausts its nuclear fuel, its core collapses catastrophically, and if sufficient mass remains, nothing can halt the collapse. The result is a stellar black hole, typically ranging from a few times the Sun's mass to perhaps 100 solar masses. At the centers of most galaxies reside supermassive black holes, objects containing millions to billions of times the mass of the Sunday. These cosmic giants appear to have formed early in the universe's history, growing through a combination of matter, accretion, and mergers with other black holes. The supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A star, contains approximately 4 million solar masses packed into a region smaller than Mercury's orbit. Even more extreme objects exist at the upper end of the mass spectrum. Quasars, among the most luminous objects in the universe, derive their energy from matter spiraling into supermassive black holes. Some of these black holes exceed 10 billion solar masses. TON 618, one of the most massive black holes ever discovered, may contain up to 66 billion solar masses. Phoenix A, located at the center of a massive galaxy cluster, might harbor an even larger black hole, with estimates reaching 100 billion solar masses. Phoenix A demonstrates the gravitational influence that ultra-massive black holes can exert. Its immense gravity affects more than 40 galaxies in its vicinity, slowly pulling them together over cosmic timescales. This cluster represents a preview of what might occur on a universal scale if gravity were to dominate once more. Given sufficient time and the right conditions, all the black holes in such a cluster could eventually merge into a single, even more massive object. Understanding these different classes of black holes and their properties provides essential context for imagining how they might interact if brought together. The process would not occur all at once, but rather through a hierarchical cascade, beginning with smaller mergers and building toward increasingly massive collisions. The physics of merging black holes. When two black holes approach each other, they do not simply collide like billiard balls. Instead, they enter into a complex gravitational dance, orbiting their common center of mass while slowly spiraling inward. This inspiral phase can persist for millions of years, even when the black holes are already moving at appreciable fractions of the speed of light. As they draw closer, their orbital velocity increases, and they begin to significantly distort the spacetime around them. The energy released during this process emerges not as light or ordinary radiation, but as gravitational waves, ripples in the fabric of spacetime itself. These waves carry energy away from the system, causing the orbit to decay and bringing the black holes ever closer. In the final moments before merger, the black holes orbit each other hundreds of times per second, releasing more energy and gravitational waves than all the stars in the observable universe produce in light during the same interval. The actual merger occurs with stunning rapidity. After the long inspiral, the two event horizons touch and merge in a fraction of a second. The resulting black hole initially writhes and pulsates, its event horizon oscillating as it settles into its final configuration. During this ring-down phase, the new black hole continues emitting gravitational waves. Much like a struck bell continues ringing, the entire process produces a characteristic signal that scientists can detect and analyze. One of the most remarkable aspects of black hole mergers involves the conversion of mass into energy. Einstein's famous equation relates energy and mass, showing that they represent different forms of the same fundamental quantity. During a black hole merger, a small percentage of the total mass converts directly into gravitational wave energy. Typically, 3 to 5% of the combined mass radiates away during the collision and ring-down phases. Consider two black holes, one containing 10 solar masses and another with equal mass. After they merge, the resulting black hole does not contain 20 solar masses. Instead, it might contain only 19¼ solar masses. The missing 3/4 of a solar mass has been converted into gravitational wave energy, equivalent to roughly 10 to the 47th joules. This amount of energy matches the total output of a supernova explosion, yet it emerges as invisible spacetime ripples rather than electromagnetic radiation. The Laser Interferometer Gravitational Wave Observatory detected the first gravitational waves from merging black holes in 2015, confirming predictions made by Einstein a century earlier. This discovery opened a new window onto the universe, allowing scientists to observe phenomena that produce no light whatsoever. The researchers responsible for this breakthrough received the Nobel Prize in Physics, recognizing the profound importance of directly detecting these space-time ripples. Among the laureates was Kip Thorne, the theoretical physicist who also served as scientific consultant for the film Interstellar, ensuring its depiction of black holes and relativistic effects achieved unprecedented accuracy. The first mergers. If dark energy were to fade and cosmic expansion reversed, black holes would not immediately rush together. Initially, the reversal would be imperceptible, with the contraction occurring at a rate far slower than the current expansion, over immense spans of time measured in billions upon billions of years. Gravity would gradually draw cosmic structures closer together. The first mergers would occur within galaxy clusters, where gravity already concentrates matter into relatively compact volumes. The Phoenix cluster, with its ultramassive central black hole and dozens of surrounding galaxies, represents an example of this process already underway. Over timescales exceeding trillions of years, all the galaxies in such a cluster would slowly converge, their central black holes eventually merging into a single object of stupefying mass. Within individual galaxies, stellar mass black holes would begin their own slow convergence toward galactic centers. These objects, scattered throughout galactic disks and halos, would gradually sink toward the deepest gravitational wells. Some would merge with each other along the way, creating intermediate mass black holes. Others would eventually reach the galactic core, where they would join the growing population of black holes clustering around the central supermassive giant. Our own galaxy provides a preview of the galactic-scale mergers that would occur throughout the universe. In approximately 5 billion years, the Milky Way and the Andromeda Galaxy will collide and merge, regardless of what happens to dark energy. This collision represents one of the most thoroughly studied future cosmic events. Computer simulations show that the merger will unfold over billions of years, with the two galaxies making multiple passes through each other before finally settling into a single elliptical galaxy that astronomers have informally dubbed Milkomeda. During this galactic merger, the supermassive black holes at the centers of both galaxies will also converge. The black hole at the heart of Andromeda contains approximately 100 million solar masses, making it roughly 25 times more massive than Sagittarius A star. As the galaxies merge, these two giants will sink toward the center of the combined system, surrounded by a dense stellar core. Eventually, they will form a binary system, orbiting each other while gradually spiraling inward. The final merger of these supermassive black holes will release approximately 10 to the 52nd joules of energy in gravitational waves. This unimaginable quantity of energy, if somehow converted to mass, would equal roughly 10 million solar masses. The waves will ripple through spacetime, carrying information about this cosmic collision to any civilization capable of detecting them. The merged black hole, containing roughly 110 million solar masses after accounting for the mass lost to gravitational radiation, will anchor the new galaxy. This scenario will play out countless times throughout a contracting universe. Every galaxy containing a supermassive black hole represents a potential merger, and with hundreds of billions of galaxies in the observable universe alone, the number of such events becomes almost incomprehensible. Each merger would add to the growing population of increasingly massive black holes, setting the stage for even larger collisions. Climbing the cosmic hierarchy, the merger of individual galaxies represents only the beginning of the hierarchical cascade that would bring all black holes together. Galaxy clusters, the next level in cosmic structure, would themselves begin merging as the universe continued contracting. These clusters contain hundreds or thousands of galaxies, all bound together by gravity and the mysterious dark matter that pervades the universe. Consider the fate of the Laniakea supercluster, an enormous structure spanning more than 500 million light-years and containing roughly 100,000 galaxies. At the heart of this structure lies the Great Attractor, a gravitational anomaly that exerts influence over our entire region of space. The Milky Way itself, along with millions of other galaxies, is slowly falling toward this massive concentration of matter. In a contracting universe, this infall would accelerate over cosmic time, Galaxies throughout the supercluster would converge, their central black holes eventually merging as their host galaxies collided. The process would likely begin with smaller groups and clusters merging first, producing ever larger black holes that would then converge on even grander scales. The timescale for such events extends to perhaps 10 to the 15 years or longer, numbers that make the current age of the universe seem fleeting by comparison. As this process continued, the black holes produced by galactic mergers would themselves merge, creating objects of unprecedented scale. The largest black hole currently known, Phoenix A, possesses an event horizon roughly 2,000 astronomical units in radius, about 32 thousandths of a light year. If all the mass in the Great Attractor region were to collapse into a single black hole, the result might contain 10 to the 17th solar masses, over 10 quadrillion times the mass of the Sun. Such an object would possess an event horizon extending approximately 30,000 light-years in radius. For comparison, this exceeds the distance from our Sun to the center of the Milky Way. A black hole of this size would dwarf anything that currently exists in the universe. Yet, in a scenario where all black holes eventually merge, even this monster would represent merely an intermediate step. The interior of such a massive black hole would present strange properties. Contrary to popular imagination, crossing the event horizon of a supermassive black hole need not immediately result in destruction. The gravitational gradient across a human body would remain relatively gentle, and an observer falling through might not immediately realize anything unusual had occurred. Only over time would the irresistible pull toward the central singularity become apparent. For a sufficiently massive black hole, this journey could last hours or even days from the perspective of the infalling observer. The universal convergence. If we assume that gravitational attractors similar to the Great Attractor exist throughout the universe, we might estimate perhaps 500 million such regions in the observable cosmos. Each would undergo its own merger cascade, eventually producing a black hole of stupendous proportions. These scattered giants would then represent the final population of black holes in the universe, separated by immense voids where galaxies once clustered. The next phase of convergence would unfold over timescales that challenge comprehension. Numbers like 10 to the 50th power years or even 10 to the 100th power years begin to appear in calculations, figures so large that they lose intuitive meaning. For context, the current universe is approximately 13.8 billion years old, or about 10 to the 10th power years. The timescales required for the final merger exceed the current age of the universe by a factor so large that writing it out would fill pages with zeros. Yet, if we imagine wading through these incomprehensible epochs, the great attractors themselves would eventually converge. Each merger would release gravitational wave energy that would cause spacetime itself to ring like a cosmic bell. The background hum of gravitational waves would grow stronger as more and more massive objects collided, until the very fabric of space thrummed with the energy of countless mergers. The penultimate mergers would involve black holes tens of thousands of light-years across, each containing the mass of quadrillions of suns. These collisions would occur at timescales matching their enormous size, with the in-spiral phase alone lasting billions of years. The gravitational waves produced would possess wavelengths comparable to the size of galaxy clusters, oscillating at frequencies far below anything humans could hear, but detectable in principle by sufficiently sensitive instruments. Finally, only two black holes would remain, each containing roughly half the mass and energy that once filled the universe. These final two titans would begin their own orbital dance, circling their common center of mass. Over additional eons, they would spiral inward, their approach accelerating as gravitational waves carried energy away from the system. The universe would contract around them, its vast empty spaces collapsing as these final objects converged. The ultimate merger would dwarf all others. The combined black hole would contain approximately 5 times 10 to the 22nd solar masses, an amount of matter and energy that once filled countless galaxies, stars, and worlds. Its event horizon would extend roughly 33 billion light-years in radius, approaching the size of the observable universe itself. In a very real sense, the universe would have become a black hole, containing within its event horizon everything that ever existed. The black hole universe hypothesis. This final state, where the entire universe collapses into a single black hole, connects to a speculative but intriguing idea in theoretical physics: the black hole universe hypothesis. This proposal suggests that our universe itself might actually exist within a black hole, and furthermore that black holes in our universe might contain universes of their own. The hypothesis does not claim that every black hole contains a universe, but rather that under specific conditions, the collapse that forms a black hole might trigger something akin to a Big Bang from an internal perspective. From outside the black hole, matter falls through the event horizon and appears to slowly freeze as it approaches, eventually fading from view. But from inside, the view might be entirely different. Some solutions to Einstein's equations of general relativity suggest that the interior of a rotating black hole could contain a region where space expands rather than contracts. This expansion, viewed from within, might resemble the Big Bang and subsequent expansion we observe in our own universe. The event horizon, rather than being a surface we might someday cross, could instead represent a cosmological horizon beyond which we cannot see. Much like the observable universe has a boundary set by the finite speed of light and the finite age of the cosmos. This idea reframes our understanding of cosmic expansion. Instead of interpreting the expansion as space itself inflating, the black hole universe hypothesis suggests we might be observing the interior geometry of an enormous black hole. The acceleration we attribute to dark energy could instead reflect properties of the event horizon as viewed from within. The cosmic microwave background would represent not the direct afterglow of the Big Bang, but rather the quantum fluctuations present at the moment of the black hole's formation. Recent research has explored updated versions of this hypothesis, examining whether it remains consistent with current observations. The mathematics of general relativity permits such solutions, though whether nature actually employs them remains unknown. If the hypothesis holds validity, then the merger of all black holes within our universe would create yet another layer in an infinite nesting structure. The resulting black hole would contain not merely dead matter, but the seeds of an entirely new cosmos with its own physical laws, constants, and structures. This new universe would emerge from the collapse with initial conditions determined by the specifics of how the parent universe's black holes merged. The fundamental constants that govern physics, values like the strength of gravity or the mass of fundamental particles, might differ from those in our universe. These new constants would determine whether stars could form in the new universe, whether galaxies would develop, and whether life might eventually emerge to ponder these same questions. The quantum considerations. The scenario described involves purely classical general relativity, Einstein's theory of gravity and spacetime. However, nature does not operate solely according to classical physics. At extremely small scales and high energies, quantum effects become dominant, and our current understanding suggests that black holes obey quantum mechanical laws as well as relativistic ones. Stephen Hawking demonstrated that black holes are not entirely black. Through a quantum process now known as Hawking radiation, black holes emit thermal radiation and gradually lose mass. This radiation arises from quantum fluctuations at the event horizon, where particle-antiparticle pairs can separate, with one member escaping while the other falls in. The escaping particle carries away energy, slowly evaporating the black hole. For stellar mass black holes, this process occurs at an unimaginably slow rate. A black hole containing 10 solar masses would require approximately 10 to the 67th years to evaporate completely, far longer than the timescales we have discussed for black hole mergers. However, as a black hole loses mass, its Hawking temperature increases and its evaporation accelerates. The final moments of a black hole's life would involve a burst of radiation as the last remnant of mass converts to energy. For a black hole containing the mass of the entire universe, Hawking radiation would be utterly negligible. The temperature would be so low as to be unmeasurable, far colder than the cosmic microwave background. Such an object would grow by absorbing ambient radiation faster than it could evaporate. Nevertheless, the existence of Hawking radiation indicates that quantum effects do influence black hole behavior, and any complete theory of black hole mergers on cosmic scales must ultimately incorporate quantum gravity. The theory of quantum gravity remains one of the great unsolved problems in physics. String theory, loop quantum gravity, and other approaches attempt to unify quantum mechanics with general relativity, but no experimental evidence yet confirms which, if any, these theories correctly describes nature. The extreme conditions inside black holes and during their formation might provide the key to understanding quantum gravity, as these represent some of the few places where quantum and gravitational effects occur with comparable strength. Observational constraints. While the scenario of all black holes merging remains highly speculative, observations can constrain whether such an event could occur. Current measurements of cosmic expansion show no sign of slowing. Instead, the expansion appears to be accelerating, with galaxies moving apart from each other at ever-increasing rates. This acceleration has persisted for several billion years, suggesting that dark energy remains a dominant force in cosmic evolution. Measurements of the cosmic microwave background provide additional constraints. The patterns of temperature fluctuations in this relic radiation encode information about the geometry and composition of the early universe. Multiple independent analyses conclude that the universe appears spatially flat within measurement uncertainties, though a slight positive curvature cannot be ruled out. If the universe is indeed closed, the closure must be extremely subtle, affecting only scales far larger than the observable universe. The behavior of dark energy remains one of cosmology's deepest mysteries. Unlike matter and radiation, which dilute as the universe expands, dark energy maintains constant density. As space expands, more dark energy appears to fill the new volume, driving further expansion in a runaway process. Understanding why dark energy behaves this way and whether it will continue to do so indefinitely requires observations that push the boundaries of current technology. Future missions planned by space agencies worldwide aim to map cosmic expansion with unprecedented precision. By observing distant supernovae, measuring gravitational lensing effects, and mapping the large-scale structure of the universe, astronomers hope to constrain dark energy's properties and determine whether its strength has changed over cosmic time. If dark energy proves to be truly constant, then the scenario of universal collapse and black hole merger appears impossible. But if dark energy is dynamic and might eventually fade, then gravity could ultimately prevail. The far future universe. Even without universal collapse, black holes will play an increasingly important role in the far future cosmos. Stars have finite lifetimes, and eventually, star formation will cease as galaxies exhaust their reservoirs of gas. The universe will enter an era where stellar remnants, black holes, and perhaps free-floating planets represent the only objects of interest. Current estimates suggest that the last stars will fade approximately 100 trillion years from now, as the smallest red dwarfs exhaust their hydrogen fuel. After this point, no new stars will form, and the universe will grow progressively darker. Black holes will become the dominant form of compact matter, slowly growing through occasional mergers and the rare capture of passing objects. Even without universal collapse, black holes within galaxy clusters will eventually merge over timescales extending to 10 to the 20th power years or beyond. These mergers will occur through gravitational wave emission alone, as the black holes slowly spiral together across the vast empty reaches of dead galaxies. Each merger will briefly illuminate the darkness with gravitational waves, providing a fleeting signal that something still occurs in the cold universe. Galaxy clusters themselves will gradually dissipate through gravitational interactions. Close encounters between objects will occasionally impart sufficient energy to fling a black hole out of the cluster entirely, sending it careening into intergalactic space. Over immense timescales, clusters will evaporate as their members escape, leaving behind only the most tightly bound systems. Eventually, Hawking radiation will become relevant. After timescales reaching 10 to the 100th power years, even supermassive black holes will evaporate, converting their mass into radiation and leaving behind nothing but a faint thermal glow. The universe will enter its final era, containing only the diffuse products of black hole evaporation dispersed across an ever-expanding volume. The temperature will approach absolute zero, and complex structures will become impossible. This represents the ultimate fate predicted by current cosmology. Not a dramatic collapse and merger, but a gradual fade into cold emptiness. Yet the black hole universe hypothesis suggests an alternative. If our cosmos exists within a black hole, and if black holes contain universes, then the story does not end with evaporation and cold. Instead, each black hole represents a beginning, a new cosmos with new possibilities. Philosophical implications. The question of whether all black holes could merge connects to deeper issues in cosmology and philosophy. If the universe is truly infinite, then the total number of black holes it contains is also infinite. Merging infinite objects presents conceptual challenges that go beyond physics into mathematics and logic. How could an infinite number of separate objects converge to a single point? The question may not even be well defined. If the universe is finite but extremely large, then the merger becomes conceptually possible, though physically implausible given current evidence. This distinction between mathematical possibility and physical reality highlights an important feature of theoretical cosmology. Scientists can construct mathematically consistent scenarios that describe universes very different from our own, but determining which scenario describes our actual universe requires observation and measurement. The black hole universe hypothesis raises questions about the nature of reality itself. If universes nest within black holes within universes, where does the chain begin or end? Some versions of the hypothesis suggest an infinite regress, with no first universe or ultimate container. Each universe contains black holes that spawn new universes, which themselves contain black holes, continuing indefinitely in both directions along this cosmic genealogy. This structure resembles certain mathematical objects, such as fractals, that display self-similarity at all scales. Just as a fractal's pattern repeats when you zoom in or out, a nested hierarchy of universes might display similar large-scale structure regardless of which level you observe. Such speculation ventures far beyond current scientific evidence, but it demonstrates how cosmological questions connect to fundamental issues about the nature of existence. The current state of knowledge. Modern cosmology has achieved remarkable precision in measuring cosmic properties. The lambda CDM model, which incorporates dark energy, dark matter, and ordinary matter in specific proportions, successfully explains a vast range of observations. This model predicts ongoing expansion with no future collapse, making the universal black hole merger scenario impossible within standard cosmology. However, science progresses through questioning established models and seeking observations that might contradict them. If future measurements revealed unexpected behavior in dark energy or detected positive spatial curvature beyond current limits, cosmologists would need to revise their understanding. The history of science demonstrates that even well-established theories can require modification when new evidence emerges. Gravitational wave astronomy represents one of the most exciting frontiers in this effort. The network of detectors worldwide continues to grow more sensitive, observing black hole and neutron star mergers with increasing frequency. Each detection provides new information about how these extreme objects behave and how their mergers proceed. Future space-based gravitational wave detectors will access lower frequencies, observing supermassive black hole mergers that ground-based instruments cannot detect. These observations will test general relativity in extreme environments and potentially reveal departures from Einstein's predictions. If quantum effects influence black hole mergers, or if additional spatial dimensions exist as some theories suggest, gravitational wave observations might detect the signatures of these exotic phenomena. Each new observation constrains theoretical models and guides the development of more comprehensive theories. The meaning of cosmic speculation. Exploring scenarios like universal black hole collisions serves multiple purposes in science. Even if such events cannot occur in our universe, working through the physics involved deepens understanding of gravity, black holes, and cosmic evolution. The thought experiment forces careful consideration of how physical laws operate under extreme conditions and over vast timescales that dwarf human experience. These exercises also reveal the boundaries of current knowledge. The uncertainties surrounding dark energy, quantum gravity, and the global geometry of the universe all become apparent when attempting to predict the ultimate fate of all black holes. Identifying these gaps and understanding points toward productive directions for future research and observation. Perhaps most importantly, contemplating cosmic evolution on the grandest scales provides perspective on humanity's place in the universe. The timescales involved, stretching to numbers that exceed the count of atoms in observable cosmos, remind us of nature's vast scope. The energies released in black hole mergers dwarf anything humans might produce or control. Yet, through mathematics and observation, human minds can grasp these phenomena and trace their implications. Whether our universe will expand forever or eventually collapse, whether dark energy remains constant or fades, and whether black holes contain universes of their own, all remain open questions. Future observations will provide answers to some of these mysteries, while others may require theoretical breakthroughs that have not yet occurred. Science progresses through this combination of observation, theory, and speculation, gradually expanding the boundaries of human knowledge. The ultimate fate of black holes in our universe remains uncertain, but the journey to understanding them reveals fundamental truths about gravity, spacetime, and the nature of physical law. Each gravitational wave detected, each black hole observed, and each theoretical advance brings us closer to comprehending these most extreme objects in nature. The question of whether every black hole could collide may never become relevant to our actual universe, but exploring it illuminates the cosmos we inhabit.